Welcome to the final week of Math 320 course videos. Last week we gave the formal definition of differentiability of functions. In this week, we will examine properties of functions which are differentiable at every point in an open interval. The keyword of the week is mean value theorem. All of the results that we will be discussing are in one way or another related to the very powerful mean value theorem. The mean value theorem tells us that if a function is differentiable at every point of an interval, then we can find a point in that interval whose derivative or instantaneous slope is representative of the overall trend of the function over the entire interval. It is in this sense that the value we found is a mean value. In this lecture, we will be focusing on the special case that the overall trend is stationary and the corresponding derivative is 0. The two theorems we will discuss are usually attributed to Fermat and to Rolle. This material appears on pages 232 and 233 of your textbook. We begin by stating Fermat's theorem on stationary points. To use this theorem, the required hypotheses are: firstly, f is defined on some open interval AB. We suppose that f is differentiable at a point C in this interval, and that f of C is either the maximum or the minimum of the range of f. Let's just recall in the case that f of c is the maximum value, this would mean that f of c is larger than f of x for any x in the interval. And in the case that f of c is the minimum value, this would mean that f of c is smaller than f of x for any x in the interval. Under these assumptions, namely that f is differentiable at c and f of c is either maximum or the minimum possible output of the function f, our conclusion is that f prime at c vanishes. Now, this conclusion should already be drilled into you in your calculus courses. A consequence of Fermat's theorem is that if the function f is defined and differentiable on an open interval, then necessarily every local maximum or local minimum is a point where the derivative vanishes. Turning this around means that when looking for local maxima or minima of a differentiable function, one can first search for roots of its derivative, and then check to see whether each root corresponds to a local maximum or minimum or not. Our emphasis in this course, however, is less on how to use Fermat's theorem to solve problems. You did lots of that already in your calculus classes. Our emphasis is on why Fermat's theorem is true. Let's go through the proof now. We will only prove the case that f of c is the maximum of the range of f. The minimum case is very similar, and I will leave it to you to figure out the minor changes needed. Step 1. By our hypothesis in the theorem, the function is differentiable at c. Using the limit definition of derivatives, we can say that the limit of the difference quotient exists. What we will do is to make use of the fact that f of c is the maximum, so that inside the difference quotient, the difference f of x minus f of c is either negative or 0, but never positive. On the other hand, the denominator of the difference quotient is positive if we approach the limit from above, and it is negative if we approach the limit from below. So, we will split up the argument into two cases. First, we treat the case of the limit from above. Based on what I just said, the numerator is non-positive, while the denominator is positive for every x to the right of c. So, the difference quotient must be non-positive itself. Using the comparison theorem for functional limits, the limit of a non-positive function will be a non-positive number. This means that the limit from above of the difference quotient is non-positive. Next, we treat the case of the limit from below. In exactly the same way, we found that the numerator is non-positive, the denominator is negative, and hence the difference quotient is non-negative. So the comparison theorem tells us that the limit from below of the difference quotient is non-negative. Since our hypothesis had guaranteed in step 1 that the limit exists, this means the limit from below must equal to the limit from above. The only way a non-negative number is equal to a non-positive number is if both numbers are 0, and hence the derivative must vanish. And so Fermat's theorem is true. Notice that to prove this theorem, we only need the derivative to exist at the point of maximum. The function can still be all kinds of crazy away from the maximum point with no yield effect. Our next theorem of today is Rolle's theorem. In the previous theorem, we saw that if a function has a global maximum or a global minimum and is differentiable there, then that function has a derivative 0 at that point. Rolle's theorem simply provides a set of sufficient assumptions for Fermat's theorem to apply. Our hypotheses are, we now have a function defined on the closed interval AB to R that is continuous on all of AB and that is differentiable on the open interval AB. The only reason we do not assume that f is differentiable on all of the closed interval is because our definition of differentiability of functions only holds if the function is defined on an entire open interval that contains the point in question. If we only have a function that is defined on the closed interval AB, the point A does not have an entire open interval around it on which f can be defined. So our definition is incapable of making sense of what it means for f to be differentiable at A. In other words, in this course, we have not attempted to give a definition of differentiability that can be used at the endpoints of closed intervals. And so, as a consequence, it would not make sense for us to try to say that f is differentiable on the entire closed interval AB. However, we cannot allow the value of the function to be willy-nilly at the endpoints. So we will assume that the function is continuous on the closed interval. Remember that our definition using the epsilon delta formulation of continuity is designed specifically to capture what happens when the domain of a function is not just an open interval. So our definitions given in this course is strong enough to make sense of what it means for a function to be continuous at the endpoint of a closed interval. At this point, you may ask, didn't we also give an epsilon delta definition of differentiation? And I would applaud you on your memory and attention. Yes, last week we did give an epsilon delta definition of differentiation. And in fact, that definition can be used to define differentiability at points not necessarily contained within an open interval. Using the epsilon delta definition all the time, however, would make a lot of the proofs much more complicated. So it is basically for your sanity and mine that we stick to only the simplest case in this course and only look at the situation with the derivative can be defined using a limit definition and not the more general epsilon delta definition. Okay, this cultural excursion aside, let's return to the theorem. So morally speaking, we want a function defined on the entire closed interval AB and differentiable at every point on it. But since we haven't defined what it means for the function to be differentiable at the endpoints, we use the next best thing we know how to define, and that is to assume the function is differentiable in the open part of the interval and continuous at the endpoints. The key condition is the final one, that f of A is equal to f of B. The conclusion of Rolle's theorem is that under these hypotheses, the derivative f prime vanishes for some point C that is strictly between A and B. Again, since we don't know how to define derivatives at the endpoints, the derivative f prime as a function is only defined on the open interval ab and not the closed interval. We should interpret this theorem as saying that if the function f is sufficiently nice and that its overall trend is stationary, going from one endpoint to the other results in no overall change of the function value, then this lack of change should be reflected in the derivatives, and so at some point the derivative should be zero. Now let's look at the proof. As I mentioned on the last slide, the key idea is to pass the heavy lifting to Fermat's theorem. Since we assume the function is continuous on the entirety of the closed interval AB, we may use the extremal value theorem to say that the function attains a global maximum at some point D and a global minimum at some point C. Now, we're not quite ready to use Fermat's theorem yet. Since Fermat's theorem requires the extremal point of the function to be inside the open part of the interval, because we need the function to be differentiable there. Luckily, we can split into cases. If at least one of C and D is inside the open part, then we can use Fermat's theorem and say that the derivative is zero there. If neither C nor D is inside the open part, this means that both of C and D are either A or B. And since f of A is equal to f of B by assumption, this means that the global maximum is equal to the global minimum. And hence, the function has to be a constant function. But since the constant function has derivative 0 everywhere, we can just pick any point strictly between A and B and conclude that a derivative is 0 there. So between the two cases, we have succeeded in proving Rolle's theorem. That's it for this lecture. See you next time.